Students, welcome back. So we saw how mass is measured in case of nucleus, and we found that one atomic mass unit is also represented as 1 U, and it is equal to 1.66 into 10 to the power minus 27 kg. So now students, masses in atomic physics can also be measured in energy units. This happens because energy units. So energy units means in electron volts usually. So they may also tell you joule, but electron volt is more common. So you see this happens because of E is equal to mc squared. So let's see how much this when converted to energy. In case of when I directly write it, it's 1.66 into 10 to the power minus 27, and C, we know what is C. It is the velocity of light, 3 into 10 to the power 8 the whole squared, like this much joules. But then the more common unit is electron volt, and so when joule is converted to electron volt, we have to divide it like this, whole square divided by 1.6 into 10 to the power minus 13. This is in MeV, or million electron volts. This happens because 1 electron volt is equal to 1.6 into 10 to the power minus 19 joules, which we already know. From there comes this. So when this calculation is performed, this amounts to 931.25 MeV. So for numericals, you can remember this. You can just write this, that this is equal to 931. This is approximately equal to 931 MeV. So here we had what mass we had taken. The mass we had taken is one atomic mass unit. So we can infer here that one atomic mass unit is equal to 931 MeV. So I don't think we'll have a problem now if masses are given in MeVs also. So this is probably, this might also come sometimes in your numericals, in binding energy and other things, or in nuclear fission. You may have to convert mass from energy unit to mass unit and vice versa. So we have to remember these things. Now I would like to move back to our slides, and as we are discussing the nuclear force, we have done what is long, short range and all these things, attractive, very strong force, but we did not look at these things called spin dependent force, then non-central force, and exchange force. Now students, what is spin dependent force? Let me see. I want to write it here. So when we talk about the spin dependent, actually spin dependent is like this. Inside the nucleus, we have got protons and neutrons. Suppose we take an element where there are 2 protons and a number of 2 neutrons. Now when I talk about nuclear force, I mean the nuclear force of attraction between these 2 protons, or this proton and this neutron and this neutron and neutron. Now the attraction between them, it is found that although it's always the same amount, it is dependent on the spin of the particles. Since you have done atomic physics, you must be aware that elementary particles like protons, electrons, and obviously also neutrons, they have got a spin, and spin is, there is a vector associated with spin, and so if a particle moves this way, we have a spin vector like this. So this spin, suppose a proton is moving in such a way that its spin is directed this way, and suppose I am talking about this proton, and let me consider another proton for which it is moving in this direction. So in this case, you see this is anti-clockwise and this is, this is clockwise and this is anti-clockwise. So this spin is this way and this one is this way, or have I drawn it wrong? I think this should have been this way and this is this way. Nevertheless, what I want to say is the spins of these 2 protons, they are directed oppositely. So we have for one of them it's like this, for other it's like this. So it has been found that nuclear force is highly spin dependent. If they are parallel, we have a certain magnitude of force. If they are anti-parallel, they are different. So we'll do these things when we learn about the different properties of the nucleus. When we'll be talking about spin, when we'll again elaborately talking about the nuclear force. So nuclear force is spin dependent. That is the meaning of spin dependence of the nucleus. Now non-central. Non-central means we know what's central force. We know that central force is a force that is directed towards the center, and we can write that F is equal to Fr. I can write it like this. So see, earlier it was found that it was thought that nucleus was perfectly spherical, but then we had no reason to believe it strictly, and experiments later on showed that there was a non-central component in the nuclear force. So that, which again pointed to the fact that means nucleus is not spherical. So that's what we mean by non-central force. Now coming to the exchange force. Exchange force is even more interesting because exchange force is a concept that arose from the field theory. So field theory, according to field theory, even in case of electromagnetic interaction, interactions, a charged particle interacts with its surroundings. Why I talk about surrounding? Because here there is the concept of field. We know that every charged particle has a field around it where its effect will be felt by another charge when brought in that field, and so there is this field, and it was, according to field theory, it was explained that a charged particle modifies the space around it. It modifies the space around it in such a way that this acts with another charge when brought inside the field via this space which has been modified by the previous charge. So this is a highly mathematical field of study, but that is the best I can tell you, that it modifies the space, and this is said to be action at a distance. The action at a distance idea came also from the fact that suppose I have an object like this. When I apply force with my hand, I bodily touch that object and then that body moves. But then in case of force like that of the Coulomb's force, what happens? I have a charge here. I bring a positively charge here. Without this first charge touching the second charge, it exerts a force on the second body. So this is said to be action at a distance. Similarly, in case of gravitational force, we know that on the surface of the earth, if I place a body, say even if there is no direct touch between this body and the earth, it gets attracted and this is pulled towards it like this. So the idea of the action at a distance gave field theory a different dimension, and so that what happened is that it was thought in according to the field theory, and it was proposed that for electromagnetic interaction between two charges took place by the exchange of a certain particle, which is called the exchange particle. And since we are not doing electromagnetic theory here, I will not speak much about this exchange particle. I will only tell that this exchange particle here is a photon, and exchange particle associated with which force? With Coulomb force, which falls under the purview of electromagnetic interaction. So in case of electromagnetic interaction, the exchange particle is photon. So based on this, Yukawa assumed that if there was an exchange force for electromagnetic interaction, if there was an exchange force in case of gravitational interaction, there must be an exchange force also acting in case of nuclear forces. And with this idea, he set out a theory which came to be known as the meson theory. So let's now look at the meson theory. According to the meson theory, any two nucleons, so by the meson theory, any two nucleons, they interacted via a particle. I'll not write here via meson theory, exchange particle, he named it the pion or the pi meson. So this is what he actually predicted. This was his theory. He did a theoretical prediction, but later on it was found that yes, actually a pi meson exists, and it was discovered. And so this pi meson or the pion, and actually there are three types of pions like this: pi plus, which is a positively charged pion; pi neutral, which is a neutral pion; and pi minus, which is a negative pion. So this is a new particle, and we will look at how this pion as an exchange particle, according to meson theory by Yukawa, gave explanation of nuclear interaction. So I would like to stop here. We'll see the rest in part C of our class.